We now move back to academics. Guillaume Rao comes from Marseille, as some of our organizers, from a very big institute called the Institut for Movement, if I'm not mistaken, which is also sponsored by CNRS, and it's one of the best place in France, I would say, to study movement. Maybe not best, but at least biggest place in France to study movement. And we're very happy to have you here in this movement topic.
Thanks a lot, and thanks for the introduction and the invitation. Good morning, everyone. So I'll talk about some things that you might have seen previously. The idea of the presentation of the talk will be to give a short overview of the different techniques or models we used to estimate the internal stress or the internal loads without having to cut the subject open and put some strain gauges inside. So how do we do that? First, as I said, we would like to estimate the internal stress during the movement. So how do we do that? By understanding how the system works and by modeling it. So how the system works, basically, you have a brain that sends signals to the muscles contract themselves, they produce some force, and you have a nice movement after that. If we are all gathered in this room, it's because mathematics is the solution to answer this question. Okay, so math is the solution, that's great. But what's the problem? Actually, that's the problem. If you look at a human body, at the inside of a human body, you have several joints, like more than 200. You have several muscles, more than 600. We call it redundancy. Basically, you have more muscles than degrees of freedom, meaning that you have more unknown than equations. In maths, it's not really good. So we use some equations where we try to explain the right-hand part of the equation, which is what we know, with the left-hand part of the equation, which is what we don't know. And you can see a little imbalance in between them. So we'll use some biomechanical models and some numerical optimization to solve for this redundancy. In biomechanics, or in sport movement in general, two types of models are used to estimate the internal stress. The first one are the ones that are used to estimate the muscle forces. That can be some complex models. And the second one, as you have already seen with Lee's presentation, are the ones that are able to estimate the local stress, the internal stress, and that are usually used done by finite element modelings. So I'll try to express these two types of model in the sport context. As for all the models, you need some data, experimental ones. So we'll have some motion capture, some mock-up. You can use you can see the markers that are the white part that are reflecting in the videos while the subject is running. You have the gray rectangle in the middle of the room, which is the force plate. And on the subject, we have some EMG data, so some muscle activations data. And we collect everything at the same time. So we ask the runner to run with different shoes. And the question is, can the shoe influence the running techniques or the running techniques and the muscle mechanics? That is the way you are running, the way you are producing your movement. We ask several subjects to perform different running conditions. So they run with two different types of shoes and barefoot. So we perform a complete motion analysis and also some biomechanical modeling to estimate the muscle forces while the subject is running. Without going too much into details, that's the typical graph we have. So we have for each muscle, each graph is a muscle, and we have the time course of the muscle force while the subject is running. And what we do is compare, for example, for different kind of shoes, the the answer or the behavior of the subject with this shoe. As you can see, if you are looking at the ankle joint range of motion, which is the way you move your ankle joint back and forth, when you are running barefoot, you have a higher amplitude of movement. So that's good, meaning that you are using more the ankle joint than with traditional shoes. Okay, so externally, when looking at the kinematics, the joint kinematics, you'll have higher ankle joint of motion. But what does it say of the inside of the body? How do you produce this higher amplitude? The results from the model said that you have less muscle stretch, which means that you have higher amplitude of the ankle joint, but less stretch of the muscle fibers. So everything, or the major part of the movement is taken by the tendon, meaning that you will have higher strain and stress within the tendon, and so some shoe features can decrease the comfort and increase the injuries based on these results. Basically, if you increase the part played by the tendon without any adaptation or learning to that, you might increase the stress in the tendon and lead to a tendon rupture or biggest like tendinopathy. So biomechanical modeling and mathematics can help in preventing this kind of injury, basically because if you are running different experiments with different kind of shoes, you can compute the internal stress and find the best compromise between the properties you want for the shoes and the outputs for the human body. This first part is dedicated to muscle and tendon, but we don't have any information on the stress and strain on the different body parts, for example, the bones or the ligaments. That's usually what we do using finite element modeling. And as Liz already presented, we also have, but for a different company, a foot model that we can drive through muscle force. So basically, that's how we do it. We use the lower part, which is what I already presented, muscle modeling to estimate the muscle forces, and the upper part is a finite element model of the foot. We combine both of them, and we drive them using muscle forces to estimate the local tissue loading. Here is what we can have as a result. If you put a shoe around the foot and you ask the model to run, you can see the full strike of the foot on the ground, and you can also see by color grading the different stress within the bones. So while the foot is moving on the ground, and what you can do, as you can see, there is a sole here with specific material properties for the materials. You can change these properties, you can change the shape, the geometries, and you can have a look at how these changes do impact the loads within the body. And using that, you can optimize the shoe features to reduce the strain within the elements. So, as a conclusion, mathematics is essential for understanding human movement, for improving performance, and also to develop sport products. And currently, so in the futures, all the works, all the subjects that have been presented here are located really close to the labs. So we need some labs to collect the data and to drive the model, which is good, obviously for academics, but which is not really good for a real life project. So basically, right now, we are dealing with either interdisciplinary projects where we try to merge different disciplines, or field-based data. And so that's two examples of this kind of projects. And you can see that it's close to the lab, so we have also some nice, nice place to go out and to do some experiments. Thanks a lot.
Yes, so very nice presentation. I had more or less the same question with the previous presentation about the simulation. What kind of physical measures are you using for the simulation, and are you considering visual information?
Same answer as before. No, so we are currently using mostly biomechanical data, so which are velocity, stiffness, material properties, and we are beginning to integrate some other parameters, mainly physiological ones, in order to better match with the subject's specific features. So. If you look at these schematics, if you want to integrate the visual information in the model, you have to have a circular model where the information are processed and taken into account to drive the model. And in our case, it's not the case. We collect some data in the lab, and we have an inverse procedure to estimate the loads within the body during the movement we observed. So it's not a circular model, it's a linear, a sequential one. We are trying to move to this circular one, mostly for clinical or pathological cases, but it's really consuming in terms of computer time, and it works for 2D models, but we know that 2D is not the reality, so it's not an easy answer to the question.
Thank you very much.